Good evening, everybody. Everybody finding a seat? We're nice and full tonight. I'd like to thank you all for braving the weather. Oh wait, that was last week. Sorry about that. That was last week that we were braving the weather. This week you chose to come out of a beautiful day and into this auditorium, and thank you for doing that. My name is John Linkstein. I'm on day 17 of my new job at the Freshwater Society. Thank you. We're here for an important topic tonight on soil health, and for those of you that are already members of Freshwater, thank you for being part of our gang of friends that work for Freshwater. And for those of you that are not yet one of our friends officially, out at the table in the entry area, there's an envelope like this. You can join Freshwater, an organization that's a nonprofit, educational nonprofit that works to promote the value and conservation and stewardship of our freshwater. What better choice could you make than to be one of our members? I want to thank our sponsors this evening for generously hosting this event for the Minnesota Office of Soil Health, which is a collaboration of the Minnesota Board of Water and Soil Resources and the University of Minnesota Water Resource Center. The Environmental Working Group, EWG, a nonprofit, nonpartisan organization that's dedicated to protecting human health and the environment, and whose mission is to empower people to live healthier lives in a healthy environment. Also, I want to thank the USDA, Natural Resources Conservation Service. Those of you old timers, we referred to it back in the day as a soil conservation service, but when I started, that's what we called them anyway. They provide for America's farmers and ranchers financial and technical assistance to voluntarily put conservation on the ground, not only helping the environment, but agricultural operations as well. So thank you to our sponsors. Would you join me in thanking them? The real deal tonight is to hear our speaker, and to move on to that, I'd like to introduce Anna Cates, the State Soil Health Specialist. Dr. Cates is Minnesota's first State Soil Health Specialist in the Minnesota Office for Soil Health, and she is dedicated in that office to improving soil health in Minnesota. Anna.
Thanks. Thanks everybody for coming tonight. I think that Dave Montgomery's work is so valuable because he's able to translate the complexities of soil science into something that's exciting for everyone. And I just learned recently that he wrote a book about salmon early on in his career, which I've really been enjoying, so thanks, Dave. Anyway, the Minnesota Office for Soil Health is pretty new. I'm pretty new to the state. I got here in January. This office is this collaboration between a state agency and the University of Minnesota, and we're working on providing education around soil health to the people who work with farmers every day. I'm just one human. I can't be on every farm field in the state, but there's a lot of people who are working with farmers every day, and I can help them have access to the best information that University of Minnesota has to offer. So look for us in the coming months. Get in touch with us. We're on Twitter at Minnesota Soil. So thanks everyone for coming tonight. Really looking forward to it.
And now just a couple housekeeping items. I'm Carrie Jennings, Research and Policy Director at Freshwater. And when you came in, you got this little bio about Dave. And on the back of it are the instructions for how you can ask questions throughout the lecture period using your cell phone or your tablet. So you can participate in Pigeonhole Live. You can practice opening it right now, because our very first poll we would like you to participate in is valuable to us because we like to know who's in the room. So you can open that poll and then find the category of, what defines you. We were interested last time. We had a lot of water resource professionals. Maybe 30% of the audience were water resource professionals, which was fascinating to us. We're happy to be of service to the community in that way. But it's my pleasure tonight to introduce Dr. David Montgomery. I have two bios here. One would be if you were all geologists. I would talk to you about him being a geomorphologist and fluvial and hill slope processes, but that's the one I'm going to skip over for the more general one. He is a He has studied everything from the way landslides and glaciers influence the height of mountain ranges to the way that soils have shaped human civilizations, both now and in the past. He's worked throughout the world, in the Cascades, the Pacific Northwest, the Andes in South America, Tibet, and the Himalayas in Central Asia. And in addition to his really expansive academic career with journal articles, he has written books that you want to read as well. The Rocks Don't Lie, A Geologist Investigates Noah's Flood, which won the Washington State Book Award, and then Growing a Revolution, Bring Our Soil Back to Life. In that book, he introduces us to farmers around the world at the heart of a soil revolution and makes the case for an agriculture that is profitable while also feeding us all, cooling the planet, and restoring life to the land. He's an elected fellow of the American Geophysical Union and also got a MacArthur Fellowship, which is kind of like geology's Nobel. So have you entered your Pigeonhole Live app and entered in your profession? Do you need lights to do that? A little bit of light would help. Maybe bring out the house lights a little bit. 2 other housekeeping items. If you turn in evaluations for this lecture, you will get a free Freshwater calendar on your way out. So trade in your evaluation for a calendar. And there will be books for sale, and Dave will be signing those up until about 9 o'clock tonight.
First of all, thank you for coming. It's really nice to see so many people here. I've been in Minnesota for about a month now and very much enjoying myself, other than a couple days last week. But I've been down at Gustavus Adolphus College working on a new book and teaching a class on science writing for the general public. This is not something that I imagined I would be doing a lot of when I went to graduate school to study, the heights of mountain ranges and things like that as a geomorphologist. But I've spent a lot of nights and weekends in the last decade working on sort of popular science books in the sense that they're not meant for my academic colleagues, they're meant for anyone who's interested in these kind of topics. And of course, I'd like my academic colleagues to think that they're really good books, but they're not the intended audience. And I spent a lot of time writing about the importance of soil for civilizations in the past and what it'll mean for humanity in the future, which is not exactly the kind of thing you might expect a geologist to spend their spare time thinking about or writing about. So what I want to share with you tonight is essentially why somebody like me would spend so much time over the last decade working on those kind of topics. And the short answer is I think they're really important, but they're also really interesting. And the way that we've thought about soil is changing, and I think we're at a pivotal place in humanity's relationship with the land for reasons that I'm going to go through as I walk you through the 3 books that I've written on it. So I'm going to try and do 3 books in 50 minutes or so. It's kind of a fast tour through my thinking process and evolution. But that one on the left, that dirt book, that's what really got me started writing about soil. So when I wrote after the salmon book, it really essentially dives into a geologist's view of the way that people have treated land over the time since the last deglaciation, the time that essentially agriculture evolved and humanity's trajectory fundamentally shifted to leading us to where we are today. It's the kind of book you might expect a geologist to write about soil. It's backwards looking. It's looking at that history. And it can be summarized in the sense of a single sentence that societies that did not take care of their soil did not last. And that's a lesson that's pretty pertinent today to our global civilization. But that middle book, The Hidden Half of Nature, is one that I wrote with my wife, Anne Baclay, and she's a biologist. And when you think about what makes healthy, fertile soil, as we'll go into, it's the marriage of geology and biology. So yeah, of course we would write that book together. It got into looking at the role of microbial life, bacteria and fungi in the soil ecology, the part of ecology that neither Anne nor I were trained in as undergrads or grad students in the natural sciences, a part that's really changed a lot in the last few decades. And it exploits our exploration of that science and how we restored life to our yard in North Seattle. And I'll tell you a little bit about that story. And we'll get to that Growing a Revolution book, which is the most recent one, that looks at the potential for regenerative agriculture, for farming that practices, intensive farming practices that can rebuild the fertility of land, the potential for that to undo the history and damage that I talked about in that first book. So I'm going to take you through my own journey in thinking about soil. And I want to start with this map that the UN put out about, 15 years or so ago of global soil degradation. Now it's painting with a really broad brush. Don't take this too seriously in terms of the pattern that you see other than the broad brush pattern. There's a lot of orange and a lot of red in the map. That's the point. There's a lot of areas of the world where the soil's been degraded or very degraded. And the methodology used to make this map, we could quibble all day with that. There's been lots of arguments. If you look at all the studies that have tried to compile how much of the world's agricultural land has been degraded so far in a way that impacts its agronomic productivity, you come up with answers between about a quarter and a third. Some answers, some people estimate even a little higher than that. The point is, it's a global problem. It's a serious problem when you think about how we would feed the world in the future. But I also want to point out that you could go into almost any of those red zones on the map, and you could find farms that are very productive and that are turning around and restoring the fertility of their land, completely doing the opposite of the first pass blush you would take by looking at this map and going, wow, we've degraded a lot of land. I like to start with this map because it's both the cause for concern, but within those red zones, within that cause of concern, there's the seeds for optimism. And if we start at the first 15, 20 minutes or so of this talk, if it's kind of depressing, well, bear with me. That's the story of what we've done to the land through history. But I'll turn it around. It gets better. I've gone from being very much a pessimist about the problem of land degradation to being very much an optimist. And it's a genuine transformation based on observations and research and so forth. So if you're depressed in the first few minutes, just hang in there. We're gonna get to a better place by the end. But where are we essentially today? The UN put out a global state of the soil assessment in 2015, just a couple years ago now, where in the executive summary, they summarized the report as arguing that humanity, the collective global us, are losing about 0.3% of our agricultural production, food production capacity each and every year due to ongoing soil loss and soil degradation. Now, 0.3%, that's not a terribly big number, is it? It's probably about what we're all getting on our savings accounts. And you have to be a geologist to appreciate the amount of time these days that it would take to add up to a real number. But if you think about it over a time scale that a geologist feels is pertinent to thinking about sustainable agriculture, the next 100 years, say, and a century is kind of round-off error on geologic time, remember. Over a century, that 0.3% adds up to 30%. In other words, we're kind of on track at a global scale with our current agricultural practices, viewed kind of broadly through thick fuzzy glasses, to degrade another third of the world's agricultural land. And if we've already degraded about a third, we're on track where maybe by the end of this century we'll be over half in terms of squandering our natural inheritance at the end of the last ice age. That's not a terribly safe place to be when the human population is projected to grow by another third in the coming century. This is why I think agriculture is going to change over the course of this century, why I think it must change over the course of this century. Fortunately, as you'll see, I think there's a way to do it, and I think the roots are starting, and that there's real cause to think that we may actually be able to reverse the pattern that I'm about to show you based on the research from doing the dirt book. So that dirt book looks backwards at societies around the world. And when you do that, when you take a look at the archaeological evidence, the soils of different regions around the world, and you put that history together, what you basically come up with is a story that soil erosion and soil degradation, and those are different things. Soil erosion is the loss of the soil as a physical body itself. Soil degradation is the degradation of its fertility, the loss of soil organic matter, the loss of its productivity, the degradation of its structure. Those are parallel things. They can act at the same time. Neither one of them is good. But those twin problems of soil erosion and soil degradation really helped undercut ancient civilizations, going all the way back to ancient Mesopotamia if we throw salinization into the mix, but also in terms of Neolithic or Bronze Age Europe, classical Greece, Rome, the southern United States. I kind of went through the whole litany of societies around the world where the geology and the archaeology had been done to put that story together, and you see a fairly similar story in many places around the world of soil degradation contributing to undercutting civilization after civilization. Now, what was it that actually contributed to that? If you read most environmental history textbooks, what you read is that deforestation led to soil erosion, which undermined civilizations. The idea that erosion has impacted societies in the past is not an original idea I thought up. There's been dozens of books over the last 200 years that have touched on that issue. But most of them have looked at deforestation as the root cause. Now, I cut my geological teeth in the mountains in western North America, where it's studying 45-degree slopes where if you cut the trees down, yeah, you get more landslides. but they don't strip the soil off whole regions of the terrain, even in the most erosive areas, as we can show, it turns out, happened in some ancient regions around the world. So I came at this problem from the perspective that, well, maybe it wasn't simply deforestation, maybe it wasn't the axe, but it was the plow that followed. And what is it about tillage? What is it about the plow that actually made it so erosive? Well, it fundamentally changed the balance of soil production and soil erosion on the land that societies use to feed themselves. And if you think about soil as nature's capital, essentially the natural capital that societies use to finance their growth and development, it's kind of like, you can think of soil the way that we all think about our bank accounts. We have income, and in the soil analogy, that is converting rocks into breaking them down into mineral matter, merging it with organic matter to make fertile soil. We have our expenses, which in the soil analogy is erosion. And we have our savings, which in the analogy for society is the soil that's sort of in the bank, if you will, on the hill slopes and on the valleys where we grow food. And if any of you have ever run the same experiment that I've done several times in my life of spending money faster than you make it for long enough, you will have demonstrated to yourself that it's possible to actually run out of money. Societies have done the same thing with their natural capital in terms of their soil. The analogy is actually pretty good. And we all know that you don't have to completely run out of money to have financial hardships. That is part of the story of many societies. Very few places actually literally ran out of soil. Although you can point to a few, like parts of Syria, parts of Libya, where today their descendants 2,000 years later remain impoverished. But the loss and degradation of soil has limited the development and stability of many societies around the world. I'm not going to go into all the examples that I go into in the dirt book. I mean, that's what books are for. You can read it at your own pace. I could be talking till midnight about all these examples. We'd all be bored. I'm going to give you essentially a couple examples. I'm going to start with classical Greece. Why do I start with classical Greece? Well, because a lot of the work had already been done by geologists and archaeologists that I could review, and I'll share some of their work with you for the next few minutes. But when you look at southern Greece, cycles of erosion and soil formation really kicked off there when the plow arrived in the Bronze Age from points farther east. And what happened is that this is a reconstruction of a cross-section across a hillside. So it's like if you took a backhoe, just dug through a hill from the ridge crest over there on the far side to the valley bottom with a little stream on the right. And it shows you the reconstruction that Tjeerd Van Andel and Chris Runnels, a geologist and an archaeologist, put together back in the 1980s about what this landscape was like at the end of the last ice age. It was an open oak woodland. So it was about 1 to 3 feet of soil on the hillsides. There was rich, dark alluvium, river bottom deposits down in the valley bottom. Open oak woodland on the hillsides. And when agriculture arrived, tillage started up at the valley bottoms and progressed up the hillsides. Where do you think they would have started farming in this landscape? Well, along the valley bottoms, because they're flat, relatively easily worked soils that have proximity to water. But as their population grew, farming spread up on the hillsides and eventually covered much of the upland landscapes. And what Van Andel and Runnels did is they put together the story of this landscape by looking at the deposits down in the valley bottom, and they documented how the soils were eroded off the hillsides and they ended up down in the valley bottom. And it didn't happen overnight, it played out over time, but it happened. They dated the deposits, they mapped the deposits. You can also find Bronze Age agricultural implements up in those hillsides labeled the maquis with the sort of the degraded vegetation, where you now have bare, rocky slopes where you wouldn't think to plant wheat. The landscape changed, but it changed slowly. It changed right out from under the classical Greeks. And Van Andel and Runnels did something else that I thought was really quite innovative, and kind of what started me in thinking about writing the dirt book is when I was reading their paper. And they looked at the human population density in the southern Argolid, sort of a particular valley region of southern Greece, and tried to reconstruct how many people lived on that landscape from 6,000 BC up to the present. And what you notice is that each one of those black dots is one of the reconstructions, and the dashed lines are sort of, connecting the dots. But when you do that exercise here, you'll notice there's 3 cycles of a rise in population, a drop, a rise, a drop, and another rise. And there's 2 characteristics to that curve. And I think they're both interesting, but one is trivial. And the trivial one, of course, is that the amplitude of those peaks goes up each time. And why is that trivial? Well, think technology. We can support more people today with our technology in the year 2000 than you could on the same landscape with, an oxen and a digging stick back in 4000, 3000 BC. There's no real mystery that with each cycle of civilization, the population was able to rise. What intrigued me a lot more is it kind of looks like there's a periodicity of a few thousand years to that curve. That the time between peaks isn't all that different. Order of 1,000 years plus or minus 1,000 years. And the question, of course, that was in my mind is what happens to the right of that curve? What happens into the future? And is this an analogy for what could happen worldwide? There's not very many places in the world where 3 civilizations have occupied the same piece of terrain. That's the other reason I looked at classical Greece, because that's where it's happened, that's where people have studied it, that's where the question got planted in my mind of, wow, could soil erosion and degradation be what's setting the tempo of the rhythm of civilizations on this landscape? And that led me off to study other landscapes around the world. But like happens more often than scientists like to admit, when you think you've come up with sort of a new angle and a new idea, you then go to the literature and find out your colleagues have beaten you to it. Well, I had the great honor of being beaten to this by the Greek philosopher Plato several thousand years ago. How's that for a brand new original idea? Because when you go back and read Plato's dialogues, he wrote about the problem of soil loss and degradation in the Greek landscape. He was writing from the peak of population in the time of classical Greece, and he was writing about the Bronze Age, when he wrote that the rich soft soil has all run away, leaving the land nothing but skin and bone. But in those days the damage had not taken place, the hills had high crests, the rocky plain of Phellus was covered with rich soil, and the mountains were covered by thick woods, of which there are some traces today. What Plato was writing about are observations like an oak tree that was on a pedestal of soil at the edge of a plowed field, where he recognized that the farmer had not built up the soil to elevate the oak tree, but the fields had eroded away around it. And he backed his inference up by looking at things like the mouths of rivers, where the rivers that were flowing out of the forest flowed clear and clean, and rivers flowing out of plowed watersheds flowed muddy and dirty. He looked at the estuaries, the deltas. The ones that were coming off of the tilled terrain had big fresh deposits building out into the Mediterranean. This is not just a problem in classical Greece. Has anyone ever been to the classical port of Rome, Ostia, in central Italy? It's not on the coast. There's many ancient ports around the Mediterranean that are now stranded miles inland. You don't build a port miles inland. So what happened? The soils on the hillsides were washed out and built those deltas out into the Mediterranean. And if you look at the ones that had more tillage, they had bigger deltas. This was a problem that is not one that was restricted to the ancient world. Now I'm going to pick on my own home state of Washington for a few minutes, because I generally find when I travel and talk about these issues, particularly in states with a large farming presence, it's better to pick on your own home state. So of course, when I talk about this in Washington, I talk about places like Iowa or Minnesota. But this is a picture of the Palouse, eastern Washington. So it's the hill country that has very erodible, loess or wind-deposited soils. And this picture captures why a geologist would look at tillage, the act of plowing, not so much as an iconic symbol of agriculture as much as an incredible slow-motion natural disaster. Because you'd notice that those little channels that are carved in that hillside, those are called rills. We call them rills because you can erase them with a single pass of the plow. If you can drop your tractor into it, it's a gully. If your tractor can erase it, it's a rill. That's a simple rule of thumb. And you'll also notice that there's no vegetation on this slope. This is a winter wheat field that was in the traditional winter wheat fallow rotation, and this is what happens if you got some rain during the fallow period, when the crops were not leafed out. And those little rills they're an agronomic nuisance, but what happens if they happen year after year? And in a winter wheat fallow rotation, they happen fairly frequently. This slide shows you a fence in that upper right-hand corner. It's also from the Palouse in eastern Washington. And the fence line was put in 1911 when this field was first plowed, and it had been essentially in a winter wheat fallow rotation for the 50 years between 1911 and 1961 when the slide was taken. And this shows you the edge of the field, and it shows you a bit of a cliff that developed at that edge of the field. How high is that cliff? It's about 5 feet. 5 feet of soil loss in 50 years is about a foot a decade. That's about an inch of soil loss every year. There's nowhere on earth that soil forms that fast, naturally. Because as I'll show you, my wife's garden got close. I've been on farms that have been close to an inch a year, but you're not turning rock into soil at that kind of a pace. I'll get back to that. The world record soil formation that I know of by nature, converting rocks into soil, is about 1 millimeter or so a year on a steep slope on the South Island of New Zealand. I know it because one of my grad students and I published it a few years back. We went to the place where we thought we could get the fastest rate of soil production, and it was fast, but it was still 20 times lower than this field was eroding. This is a serious problem if it plays out over the long run. Now, I also hope you're sitting there thinking, but yeah, Dave, isn't this a pretty extreme example? And my answer would be, yes, of course it is. That's why I use it. It's the most extreme example I could find. It is not typical. So how typical is it? That's the real question. I mean, I like this because the extreme example focuses the importance of the question, but the real question at a global level is not what's happening in one corner of one random farm in eastern Washington. It's how fast can you do this over a whole region? And for that, the example that I'll share with you is the southeastern United States, a region that runs from Virginia up there in the upper right-hand corner to Alabama in the lower left. And that gray noodle is the Piedmont region, or the hill country. So it's not the broad coastal plain, and it's not the rocky spine of the Appalachians. It's the sort of the soil-covered hill country that was one of the original breadbaskets of the American colonies. And what this shows you is the amount of historical soil loss that was mapped by colleagues back in, I believe, the 80s when they mapped it. It's not my original work, but what they showed was, more than 4 inches and up to 10 inches of soil loss across pretty much the whole region, in some places more than 10 inches of soil loss. Well, how big a deal is that? Well, when you go back and you read the original journals of the plantation owners and farmers who were first working this land and clearing the forest to farm it, they reported about 6 to 12 inches of rich black earth over the orangish subsoil. So if we could erode off 1/3 to all of the topsoil across a pretty broad region of our country and do it in just a couple hundred years, think what the Greeks could have done with a 1,000-year run at southern Greece. Think what the Romans could have done with an 800-year run at central Italy. It starts to put into perspective that the problem of regional soil loss and soil degradation can really add up over time. Awkwardly, that time scale appears to be centuries, and we're not that good at managing things that happen that slowly. And you look at the history of a lot of regions around the world is the long-term slow degradation of their land. And the American Southeast was a big player of that. We're not taught that the degradation of the eastern seaboard was part of what led to the push west and helped set up the Civil War. I read about all that in the Dirt book. I'll spare you the details, but what I do want to show you is what it did to the soil. This shows you 2 soils off of a tobacco plantation and the neighboring forest in that gray noodle from North Carolina. And the one on the right is a soil that I dug up from a conventionally managed tobacco plantation. The one on the left is from a farm that had what's now a forest with trees about 1 meter or so in diameter, the biggest trees I've seen in that region. It was abandoned about 100, 120 years ago or so, had been a farm, reverted to a forest, and the difference between these 2 soils is not the parent material. It's the same geology. It's not the climate. They're right next door to each other. It's how they've been managed for the last 100 years. Which of those would you rather be farming? The khaki one that looks like California beach sand with some crusty salt in it? Or the more sort of chocolatey one that has the organic matter in it? There's a clear difference in fertility that you can see. And basically that translates into carbon in the soil. Is the difference, the color difference. And I'll show you a few slides that have that kind of color difference as we go. This is essentially the analogy for what we've done on farmland across North America, but this is with the forest running it in reverse. The soil on the left was probably a lot closer to what the native soil of this region was like. What we've done is turned it into the stuff on the right. That's part of what that UN report was talking about that I mentioned earlier. It's also a fairly decent analogy for what we've done on agricultural land around North America. It's a paper that came out 3 years ago now that looked at the North American soil degradation and tried to sort of add up and characterize and quantify what had happened on North American agricultural land. And the bottom line they came up with was that our agricultural lands averaged, with thick fuzzy glasses across North America, we'd lost about half of our SOM, soil organic matter, carbon in the soil. That's the soil degradation problem right there. In a way, we've run down about half the batteries, if you believe this paper, of our agricultural land through our farming practices averaged over the country. And that's not simply a North American problem. How many of you had coffee this morning? No, come on, more of you did. Yeah, okay, that's better. This is from the heart of Costa Rican coffee country, and in writing Growing a Revolution, I'm going to skip ahead a little bit and then come back to my main story. I went down to visit farms in coffee country to look at farmers who were regenerating the fertility of their land. What I saw, though, when I first drove from the ridgetop into this valley and looked down in it, was a river flowing the color of the slide on the right, flowing orange. Rivers supposed to flow orange? No, they're supposed to be blue, right? You're supposed to be clear, you're supposed to be able to see the gravel in them. No, these were shallow mountain rivers flowing bright orange. The soil was literally bleeding off the landscape. And when I got out and started looking at some of the coffee fields, it was fairly clear what had happened. That one on the right is a photograph of a road cut, and road cuts are geologists' best friend. We love road cuts because they let you see a window into the subsurface. And you'll notice that there's something missing from the soil in that coffee plantation. The topsoil. It's that orange subsoil to the surface, to the little thin mat of organic matter at the top. But the topsoil's gone in just 100 years. This valley's only been farmed for 100 years. You drive to the immediately adjacent area where there's still the native forest, you find soil like that on the left-hand side. Same geology, same region, the only difference is the management. You still have about a foot of topsoil on top of the subsoil that you can see peeking out underneath my notebook there. This is another analogy for what's happened to soils around the world. So in researching the dirt book, I basically tried to address the question of, well, how typical is this sort of magnitude of loss in a problem? And so I did something that's gotten kind of hard to get students to do these days anymore, and that is I went to the library. It's this wonderful place full of these archaic things known as books. And in those things, you can find data on all kinds of studies that have been done to actually look at things like how fast do farms erode, how fast do native forests erode, how fast do mountains erode over geologic time, how fast does soil build. So I went and spent about a month, actually about 3 weeks or so, compiling all the data that I could find, and I put together a paper for the Proceedings of the National Academy of Sciences that quantified all that. And I'm going to spare you all the details of it. I compiled, I think, about 1,500 research papers to put the story together. If you're interested in the data, that reference at the bottom, there's an Excel spreadsheet with all the data that I compiled. Take it, use it for your theses or book reports or whatever. No one should ever have to compile that again. That's why you put it out there. But the bottom line is that when you look globally around the world, based on sort of agricultural erosion rates, I think it's pushing 500 separate studies, soils around the world from tilled fields, from what I call conventional agriculture, we're eroding at a pace of about 1.5 millimeters a year, that red number at the top. That's kind of a slow number. Your fingernails grow faster than that. You know, it's just kind of boring to watch something that happens at a pace of 1.5 millimeters a year. You know, the San Andreas Fault moves 10 times faster than that. And the problem with that, of course, is it's hardly boring when it eventually does move, because it moves all at once. But the key is that if you're losing 1.5 millimeters of soil a year, it takes less than 20 years to erode an inch of soil. If you look at the pace that nature builds soils on average around the world, it's that blue number on the bottom. It's more like about 2% of a millimeter a year, which means that it takes 1,000 years to make an inch of soil. Now, I wouldn't put too much stock in the precision on either of those numbers. The thing to notice is the difference is orders of magnitude. Doesn't matter if either one's off by a factor of 2. They're still way different from each other. That's the problem, is that when we disturb the surface of the soil with tillage, we lose the soil faster than it forms. And that can only go on for so long. Now, I've given you all the information that it would take for you to calculate for yourself the thing that I was interested in thinking about when I started writing the dirt book, and that's what sets the longevity of agricultural civilizations. Because if you take that net soil loss of about 1 millimeter a year, and I'm being conservative because I could argue for 1.5 millimeters, that millimeter a year soil loss means you could erode through a typical 0.5 meter to 1 meter, 1 to 3 foot thick soil in just 500 to 1,000 years. That's kind of that same time frame that classical Greece went through on its periodicity of civilizations. But I also hope that you're sitting there thinking, but what about Mesopotamia, the Tigris and Euphrates rivers? Haven't they farmed there for thousands of years? The Nile in Egypt, haven't they farmed there for thousands of years? The rivers of lowland China, the big alluvial rivers coming off the Tibetan Plateau. How about the Indus and the Brahmaputra in India? Haven't we farmed there for thousands of years? Yeah. And what's the common element in the geography of all those places I just mentioned? They're on big river floodplains. And anyone who's driven by St. Peter lately knows that what happens when a river floods, the floodplain gets inundated. And do floods just deliver clear, fresh water? No. They're full of silt, sand, tires, cars, whatever was eroded from upstream gets delivered downstream and can be deposited on the floodplain. So what is it about floodplains that allowed farming to thrive for thousands of years in these classical examples of ancient hydraulic civilizations? Well, how thick is a grain of sand? About 1 millimeter or 2 for medium to coarse sand. How fast do the world's agricultural land erode typically under plow-based agriculture? Well, around about the same number, about 1 millimeter or so. In other words, if you just deposited a single grain of sand with annual flooding on a floodplain, you could virtually offset the long-term detrimental effects of the plow if all we're talking about is the loss of the soil itself. Organic matter is a different story. But this means that there's a resilience to the geography of floodplains that's not shared by the hillsides outside the valley bottoms. And so the story I put together in Dirt looked at how once farming practices leave the floodplains and ends up on hillsides, societies that come to depend on those areas for food production, the clock is ticking if they have erosive farming practices. That concludes the depressing part of the talk. Because as you might imagine, writing the last chapter of that Dirt book was kind of difficult. I'm not inherently a pessimistic guy. And yet, you look back through history, and it's a kind of a depressing story. I pulled the elements of optimism I could out of that book, but I started wondering, is soil restoration possible? Could we actually reverse the historical pattern of decline that had impacted society after society in the past? And I really started to clue in that the answer was an emphatic yes, in a fairly unusual place to think of a geologist doing field work, and that was in my own yard, in the garden that my wife was making. Because Anne is a biologist. I think of her as a plant whisperer. I'm not allowed to have office plants anymore because apparently you have to water them. And she can bring plants, even my office plants, back from the brink of death. But we bought a house in North Seattle back in the 1990s, thankfully. And it was, she wanted to put in a garden. Because one of the attractions was it had this side yard that you see here off on the edge of the house. And it came with what we called an old-growth Seattle lawn, which is about 6 inches of tangled roots. And when we pulled that lawn off to start working on the garden, we discovered we had this incredibly rich black earth that gives Minnesota's soil a run for its money. Yeah, no, we had crap earth. We had crap dirt. It was glacial till, which I don't know, around here you probably know something about glacial till. In Seattle, a lot of our geography is shaped by glaciers when a wall of ice came out of British Columbia, moved hundreds of miles to the south from 17 to 15,000 years ago, and that ice was depositing sediments in front of it, then it overran its sediments and compressed them into nature's concrete. This is what our soil was like when we pulled that lawn off. And you might wonder why a geologist and a biologist did not think to dig a soil pit in the yard when they bought the house. We got the attic inspected, we got the basement inspected, we got some bucks knocked off the price of the house to fix a few things. We didn't think to lift the hood of the lawn and look underneath. But the good news is that Anne didn't think of it either, so. But she did think of how to fix our soil. she embarked on what we called her organic matter crusade. So she painted up her wheelbarrow to make it go faster, and because we all know that works, right? And she convinced local arborists to give us their wood chips when a limb would get knocked off. She basically brought organic matter from our neighbors. We'd rake up our neighbors' oak leaves in the fall and take them to our house. They were like very happy to have us come over and do it. They didn't realize we were stealing fertilizer. We were not doing them a favor. And that we weren't doing them a favor is easily seen by the relative size of the vegetation in our 2 yards now, that's 15 years later. But we started composting our vegetable scraps. We got a worm bin. We started composting and mulching with some stuff called zoo dew, which is as close as you can get to having manure in the city, because it's actually composted herbivore manure from the Seattle Zoo. They hold a lottery every year for gardeners where you send in a postcard, and if they draw your postcard, if you're the lucky one they draw, you get to come and fill up whatever size vehicle you can get to the zoo with as much as you can put in it. First year we won, and I was like, okay, fine, you can borrow my pickup, and loved the stuff. It was wonderful compost. Second year we won again. We were starting to think we were really special. The third year we won, we started to realize that you always win the Zoodoo lottery. But it's wonderful stuff. So, what did it do to our soil? That's the real question. The soil we started with is the stuff on my right, the right hand, your left on the screen up there. That's what we started with. It had about 1% or so of organic matter. The stuff in the other hand, my left hand, your right hand side of the screen, that's what we have now in our vegetable beds. And of course, it's the best soil on our lot. That's why I'm showing you the difference. But even the worst soil on our lot now that we have planted plants in is pretty close. It's between about 8 and 10% organic matter. Some of the vegetable beds are even higher. What was the difference? All that composting and mulching. We didn't dig anything. We didn't till. We basically kept adding organic matter. And it would disappear, and we started wondering, well, what's happening to this organic matter? We noticed our soil starting to change colors after just a couple years, and we started to think, oh, what's happening here? And we started to look into the literature, and re-engage with the soil science literature that we'd last seen in graduate school. And we realized that, we were not the ones doing most of the work transforming our soil. We were feeding the ones that were doing most of the work, and it was trillions of microscopic organisms in the soil, and the worms and the beetles and the things that were tearing up and breaking up that organic matter and consuming it in the cycle of eating and sort of an orgy of life and death, if you will, of recycling that organic matter into organisms in the soil. So we were adding the compost, and bacteria and fungi were ultimately breaking that down, and then nematodes and protozoa and microarthropods were consuming those bacteria and fungi and excreting the remains into the soil. So clumps of bacteria like that one up there in the upper left, or fungi like the little balls with their little hyphae sticking out in that root hair in the upper right, those were ultimately the things that were breaking down the organic matter. And then that nematode in the lower left, you can think of as a vacuum cleaner for bacteria. And the microarthropod on the right also likes to eat fungi and bacteria. And those things, what does anything do with something that eats? Well, it metabolizes it and then excretes the remains. The remains, the bodies of microorganisms that have consumed organic matter in the soil are rich in most of the nutrients that it takes to grow new plants. They're basically fertilizer bombs, fertilizer bags. And so when they get eaten and consumed, it's like opening the bag, and when they're pooped out by the organisms that consume them, it's basically just the same way that cattle manure a field at the surface of it. These organisms are manuring the land from within it, actually in the soil, right by the roots of plants. So we started looking into what's happening in the world of soil ecology, again, after about a 15-year hiatus out of grad school. And we'd all been trained to think about, we know that plants take carbon dioxide from the air, mix it with water they bring up through their roots to build their carbohydrate backbones of their bodies. They give off oxygen, thankfully. But the thing that we started to notice that really surprised us were these papers that kept referring to exudates, compounds that plants push out of their roots into the soil. And we had been trained to think of roots as straws that take up nutrition from the soil into the plant. Turns out it's not wrong, it's only half the picture. Roots are two-way streets. There's stuff flowing out of the roots into the soil and stuff coming into the plant. It's a two-way highway. And what are some of the kind of things that are in those exudates? That's when we started to really get interested, because it turns out that plants are pushing out carbohydrates into the soil, they're pushing out proteins into the soil. There's even papers that have documented they push out lipids, fats, into the soil. What does that sound like to you? Carbs, proteins, and fats. That's food. Why are plants pushing out food into the soil? Well, they're not doing it just to be nice or to be wasteful. Nature is brutally efficient. They're pushing out food into the soil to basically set the banquet table for microbes in the soil in a zone called the rhizosphere, which is Greek for the zone around the roots of plant. And why are plants setting a buffet out for microbes in the soil? And if you want to find a whole lot of life in the soil, look around the roots of a plant. That's where you'll find an awful lot of bacteria and fungi. It's one of the most life-dense zones on the planet. Because those plants are pushing out exudates out of their roots, that food into the soil, and it gets consumed within about a millimeter to a centimeter of where it goes out into the soil. It doesn't make it very far. And what happens, what do those bacteria and fungi do with those exudates? They metabolize them, and they turn them in turn into things, some of which have great benefit to the plants. Not all, but when we read papers that documented that I think it was bacteria, if I'm remembering this correctly, in the soil were taking plant exudates and turning them into plant growth promoting hormones that the plants then took back up. We were like, okay, basically this is a classic example of a symbiosis where the plants are basically pushing food out into the soil, and they've basically offshored their chemical factories to microbes that are consuming that food and turning it into things that actually help the plant grow so the plant can grow more food to share with the microbes. It's a symbiosis. And it turns out that those kind of symbioses with soil life and plants turn out to be fairly common. You go back and you look at the earliest fossils that we have of land plants, and there's mycorrhizal fungi wrapped around their roots. These kind of partnerships, these symbioses, go back to the colonization of the continents by plants. They're ancient. It's kind of how nature, it turns out, seems to work. And this just shows you an example of what Anne likes to call fetching fungi, where you've got a fungal hyphae going out in contact with soil particles. Notice those little holes in the soil particles. Fungi can actually prospect individual particular elements out of the soil, bring them back and trade them to plants for a cut of the sugary exudates that the plants produce. Now, why do fungi do that? Well, fungi can't photosynthesize, can they? I can't say photosynthesis. They can't photosynthesize. And that's a real disadvantage for something. What plants can do is they can eat decaying organic matter. What fungi can do is they can eat decaying organic matter, or they can eat the exudates from plants. Plants have a monopoly in photosynthesis, but the fungi can actually work as root extensions and as the miners and truckers that get mineral micronutrients out of the soil particles and trade them to the plants. Thinking about the soil through that kind of a symbiotic perspective gives you a whole different way to think about soil life and ultimately to think about how you grow plants. And I'm not just making this up. There's studies, this one particular one is actually from Japan, but it looks at basically the uptake of phosphorus, of P, for plants that were, for onions, I believe they were, that were either a control with no inoculation by arbuscular mycorrhizae, fungi. But notice the differences in the phosphorus uptake for the zero arbuscular mycorrhizae colonization over there on the right. The top number, 24.9 picograms of phosphorus per plant. You got 10 times as much if you had the right fungi in the plant. The soil was the same. Same amount of plant available phosphorus in the soil, but you're getting 10 times as much if you have the fungi in the soil to actually go and get it. Same way that if you have a phosphorus mine, but you don't have any miners or truckers to deliver it, you're not going to get much out of it. This is a different way to think about plants and their relationship to the soil than we've traditionally have. And there's connections to plant defense as well. There's studies that have shown that when insect herbivores will munch on a plant can send out chemical signals actually through the atmosphere, through its leaves, or also through exudates into the soil that can recruit particular microbes that will consume those exudates, produce metabolites that are either taken into the plant to repel that insect pest or taken into the plant and triggering the plant to produce another compound that then repels that particular insect pest. These are evolutionarily honed relationships, every bit as complicated and tailored to the ecological particulars of the species involved as what we see in terms of like pollinators and plants above ground, the world of nature we know and understand with our own senses. But we haven't really understood this stuff until fairly recently, in part because it happens in what Ann and I called the hidden half of nature, that part of nature that's too small for us to see with our senses, it's microscopic, and it's underground, out of sight, out of mind in a sense. It's very difficult. If you think about studying the ecology of microorganisms, it's hard to think about how to do it. What opened the door to doing that was gene sequencing technology, which is not all that old in terms of scientific into the last few decades. Now, what this all leads us to is different ways of thinking about how to actually grow plants, because I hadn't really thought much about plants having a diet before I helped write this book. But I now think of sort of two end-member diets that Ann and I call the fertilizer diet versus the soil health diet, with the idea being that we know that you can grow big plants and high yields by adding a lot of the major elements that you need to grow plants, NPK being the classic three. So you can have an organic matter depleted soil like that over on the left, and with enough fertilization, you can grow big plants with high yields. But what do you miss out on? Well, if you basically give a plant all the major elements that it needs for growth, it tends to become what Ann and I termed couch potato crops. They basically relax their exudate production, because I mean, why bother setting out that banquet table if you're already growing big? And so they miss out on the doses of mineral micronutrients, which has implications for us when we eat them. But they also have received fewer of the beneficial microbial metabolites that those microbes that are produced by consuming those exudates would offer to the plant. Conversely, if you have a plant that's growing in an or life-filled organic matter-rich soil, you won't be needing as much NP and K to coax the same kind of growth out of it, but you'll also get more mineral micronutrients and more of the beneficial metabolites, because you have all those microbes working for you in terms of growing plants. And I don't think it's any coincidence that the global sales of pesticide went up after the global sales of fertilizers early in the 20th century, because we effectively dismantled plants' native defense systems. These are the kind of things and questions and suspicions that led me to then research Growing a Revolution, the third book in what Ann and I call our Dirt Trilogy. Now, I basically took 6 months off of my job at the University of Washington and traveled around the world to interview farmers who had already restored fertility to their land, because I basically wanted to find out what were the commonalities, what are the common elements among farmers who had done basically to their farms what Ann had done to our yard. And to cut to the answer, and I'll show you examples of a few farmers in a minute, the farmers that had been very successful at restoring and rebuilding the fertility of their land shared three common things, which turn out to be the principles of conservation agriculture. They used minimal or no disturbance of their ground. Things like no-till. You heard something earlier today about strip tillage, which could fall under the minimal tillage, but the idea is like disturb the ground as little as possible. Maintain a permanent ground cover. That translates into cover crops. Don't do what I showed you in the Palouse. Don't leave your fields naked. And have a diversity of crops. Now, what is it about those three things that actually that make it work? That's why all those little microbes are up there on the screen. If you thought about a recipe for cultivating beneficial life in the soil, you would not disturb them. That's the first one. You would feed them. That's the second one. And for a resilient community, you'd want a diversity of life in the soil. And you get that by having a diversity of exudates and diversity of crops in a rotation. Why is the diversity important? Well, think about how utterly dysfunctional an entire university made of geologists would be. We'd have great arguments, but we'd starve to death. And if you think about how we've taught agriculture for the last 100 years, it's the opposite of these three principles. We'll get back to that. But those general principles translate to, what I found is that those principles translate to settings around the world. And I visited West Africa, Costa Rica, the Dakotas to Pennsylvania, up into Canada. I wanted to visit more parts of the world, but I basically ran out of money before I could do that. So if there's any funders in the audience who would like to support more of this work, feel free to talk to me afterwards. But what I found is that the basic principles applied everywhere I went, but the specific practices people used to implement them were different everywhere I went. And that's a really important message to make. There's no silver bullet to rebuilding soil health. It's got to be tailored to the land, to the economy, to the crops, to the farm in question. It's really hard to prescribe detailed practices that follow these principles that would work everywhere. And in defense of that, let me show you, I think, 4 farmers who were all very successful at rebuilding the soil fertility of their land, but who had used different practices. First, I want to share with you is Dwayne Beck, who runs Dakota Lakes Research Farm through the University of South Dakota. I wanted to visit his farm first because the area of South Dakota where he farms is on the cover of my dirt book. I used a classic Dust Bowl era photograph. He's basically been spearheading an effort there to adopt no-till practices, and they've basically solved the blowing soil erosion problem in the regions that he's had a great influence on. They've adopted no-till, cover crops, and complex rotations, not all at once. They figured out a system over a few decades of experimentation, but they've gotten to a point where they're all now doing all 3 on his farm, and that's allowed him to reduce the use of diesel, fertilizer, and pesticide by more than half. Now, what are the big input costs on a modern farm in the U.S.? Diesel, fertilizer, and pesticide, and we could throw in patented seeds if we wanted to. But, I'm happy stopping with diesel, fertilizer, and pesticide. If you can cut all that by half, that's a big savings. So what happened to his income? What happened to yields? Well, check out the numbers. These are sort of average numbers that he reported to me. There's more that I report in the book for more detailed things, but basically their yields didn't go down, they went up. When they restored fertility to their land, their costs went down and their harvest went up. That's a recipe for optimism. That's a recipe for wider adoption. This is when I really started to turn into an optimist in this kind of an issue, and I started to realize that the market forces that are operating on farmers today are such that if you can cut their input costs by a change in practices but maintain their yields, that's a recipe for bigger, better adoption. Now, Dwayne was working with farmers that were up to 20,000 acres. These were big farms, some of them very technologically advanced. What I asked him when I left was how well would the practices that he was working with translate to subsistence farms in Africa? Because that's where the real problem of feeding the world for the next century lies. That's where we expect the population to grow at a global scale. And he said, well, don't ask me that, Dave. I'm not a subsistence farmer in Africa. How would I know? Go talk to this gentleman here, Kofi Boa, who I had met at a conference and that Dwayne was familiar with. And Kofi runs the Center for No-Till Research in Kumasi, Ghana. That's equatorial West Africa. And notice his hat. Got dirt, get soil. I got to his farm and I was like, I like this guy. And after I spent 3 days with him having him show me what he'd done to his region, I liked him even more because he's transformed the farms in his region of Ghana by teaching them to go from their traditional slash and burn style of agriculture, which had degraded their land to the point where they had a few percent organic matter. And he taught them how to adopt no-till practices, integrate cover crops into their system, and they get their diversity in because they're operating small farms and they're operating them by hand. So they'll grow 6 to 8 crops in the same field at the same time, all interplanted. And they can do that with their system. What did it do to erosion? Well, look at the numbers. It basically turned erosion off. It got erosion down to close to what's probably background rates, although we don't actually have data on that there, but it dropped erosion rates by a factor of 20 or so. What happened to their yields? Well, their corn yield tripled and their cowpea yield doubled. That's as good as the Green Revolution did. But this is without any inputs. And why is that so important for subsistence farmers like the ones that Kofi works with? Because there's a really simple reason that the Green Revolution bypassed them. They don't have any money. They can't afford to buy fertilizer. The people that actually profited in regions like this from the Green Revolution were the larger farms that were then selling food to people in the cities. It wasn't the rural farmers. What Kofi did is he taught them a way to farm that actually used the resources they had, which was their minds and their labor and their land, to improve their soil in ways that improved their bottom line and helped lift them out of, it helped lift them economically. It's a wonderful treat to walk around his village with Kofi because everybody likes him, because now almost everybody in the village owns their own farm, whereas when he was starting to teach them these methods, they almost all rented. That is is progressive development. The third person I'll share with you is David Brandt, who runs Brandt Family Farm in Carroll, Ohio. He's standing in a cover crop field modeling one of his tillage radishes, and he grows corn, wheat, and soybeans for the North American commodity markets. He's a conventional farmer, but he doesn't only grow corn, wheat, and soybeans. He also grows very diverse mixtures of cover crops in between his cash crops. And he started no-till farming back in, I think it was the late 60s when he came back from a stint in the Marine Corps in Vietnam. And he had access to no-till equipment, so that's what he started with. He liked what it did to soil. He then progressively added cover crops and diversity over time. But check out the color difference in the field he's standing in and his neighbor's field in the background past that car there where the radish is kind of pointing to. Those yellow soybeans back there kind of look a little sickly. Notice the green bits within the yellow soybeans. Those are glyphosate-resistant mare's tail weeds. They've been sprayed 3 times this year. You cannot kill them. They're a yield drag on his neighbor's farm. David was kind enough to sort of walk me through what he estimated to be the economics of his farm and his neighbor's farm. On his neighbor's farm, it's fully conventional. They use full tillage, so they burn a lot of diesel. They're using 200 pounds of nitrogen fertilizer, 2.5 quarts of Roundup per acre. They were basically at $4 a bushel for corn in 2015 when I was there. His neighbors were losing $100 an acre. They would have been better off planting a single pumpkin, harvesting it for Halloween, selling it for $6, and going to Florida for the rest of the year. It's got a crazy business model that the harder you work, the more money you lose. And there was a study of farmers in Iowa, in a neighboring state, that same year, that showed that 24% of Iowa farmers lost more than $100 an acre on corn. It's not just David's neighbors. Now, David, who's been doing no-till for 44 years, who's added cover crops about, 15 years ago or so, and is now experimenting with these diverse rotations. He doesn't till at all, so he saves diesel out of the gate. He's using about 1/8 of the nitrogen and less than half of the Roundup. He's not an organic farmer. But I started to tease him that he was organic-ish. Because he's not using anywhere near what his neighbors are using for inputs. And that makes him save money. And he likes that, which is why he does it. He also likes what it does to his soil. And basically, in that same year that his neighbor was losing $100 an acre, David was harvesting more, so he was spending less, had a higher yield, and he was harvesting $400 per acre profits. That is a better business model. Why was he able to do it? This compares the soil that David had in the year right before I visited him on the left, labeled 2014. That's the soil in the fields that we were just looking at. The one labeled 1971 is it's similar to what David had in 1971, but it's off of his neighbor's field today. Look different? It's the same Cardington clay soil, but those color differences, may sense a theme here in where I've been going. That's the same kind of difference that we found in our yard. Same kind of difference in that from those tobacco plantations. And the difference is carbon. The difference is soil organic matter. One is fertile, and the other you need fertilizers to grow high yields in. And it is not a coincidence that David just purchased his neighbor's field. And he's planning on turning the khaki stuff into the brown stuff. The last farmer that I'll share with you is a guy named Gabe Brown. He has been following similar kinds of principles as these other people that I've talked about, but he's also been adding another element, and that's livestock, which is why he has a cow on top of the sign for Brown's Ranch. And he proudly wears the Regenerative Agriculture label. He also has a really good new book out that I highly recommend. But what he's been doing, I'll give you a short treatment of Gabe's farm because they're getting kind of late on time probably, but what Gabe has been doing is he's been bringing cattle in he's been restoring native prairie with intensive rotational grazing, but he has also been using livestock to restore the soil on some of his cropping lands. And this shows you a field that he was using as a market garden for his for selling food at the local farmer's market. And what he would do is he'd bring the livestock in to graze off the cover crops. So instead of using an herbicide or a roller crimper to terminate his cover crops, he was letting his cattle eat them and then poop them out right back in the same spot. And that essentially uses the cattle as self-propelled methane digesters to produce bovine exudates that accelerate the process of soil building. And what'd that do? Well, the soil he's holding up in his right hand there, that's the soil from the field I just showed you. It's rich black earth. The soil in his left hand, that's the soil from his neighbor's organic farm. Right next door, same soil type, same climate, similar crops for the most part. What's wrong with his neighbor's organic farm? Well, the problem is not that they're organic. The problem is that they plow too much. And that can limit your ability to develop soil organic matter. These soil building principles, these soil health principles, have something to offer both the conventional and the organic farmer in terms of how to actually improve soil quality. And Ann and I boiled down the sort of principles that seem to apply to us in this global review as boiling down to ditch the plow, cover up, and grow diversity. That's kind of a recipe for building healthier, fertile soil. And you might put a little asterisk on there and going, well, and if you want to accelerate it, maybe add cows. And you don't have to just take my word for the fact that it seems that this actually works economically. Now, the challenge, I think, is figuring out how to tailor the kind of right practices for the economics of any particular farm. But Claire Lacan and Jonathan Lundgren put a paper out in the journal Peer J, I think it was a year ago, maybe 2 years ago now, where they looked at pairs of conventional and regenerative farms across the American Midwest, and they looked at the economics of it. And the way you read these graphs are you've got total revenue and cost over there on the left. The bar chart things are conventional farming on the left, regenerative on the right. And the height of the total bar is how much income there was per hectare. So the regenerative ones had more income by a few $100 per hectare. But what's equally important is you subtract off the costs, and they're itemized in those color bars. Notice that the fertilizer cost on the regenerative one was about a third of the fertilizer cost on conventional. And that was a big piece of the difference. What's left as profit are the white bars. The one on the right is not quite twice as big as the one on the left. We need to stop thinking so much about yield and start thinking more about profit in evaluating the efficacy of farming. Because I think we're at the point now with commodity crop prices so low and input prices so high that if we start thinking about it through the lens of profit, which any reasonable business person would do looking at it independently of how they think about farming, regenerative practices are starting to look pretty good. The other thing I found really interesting is that Jonathan Lundgren is an entomologist. So they didn't just look at the economics, they looked at the pest abundance on these conventional and regenerative farms. And you'll notice that the pest abundance on the regenerative farms looks to be about 1/10 of what the pest abundance is on the conventional farms. Now, which of these farms was receiving the pesticides? It was the conventional ones. They don't put on the label, guaranteed to increase your pest by 90%. But that's what Jonathan and Claire found. Now, why would that be? Well, because when you spray broad spectrum pesticides, you're not just killing the pests, you're killing the things that eat the pests. And there's more predators out there in the world than there are pests. What comes back fastest when you plow a field and don't seed it with any crop? The weeds. What do you think happens in the world of pests? What happened when we killed off all the wolves in North America? The deer exploded. That's how ecology works. You take out all the predators, you get a boost, you harvest a crop of pests. Then you need more pesticide. Does that sound like a recipe for dependency? So benefits of building healthy, fertile soil, as I see them, I put higher farmer profits at the top of the list because I think that's incredibly important for getting these ideas to be adopted. We need more profitable farms. It appears that once the soil is restored to fertility, you can harvest comparable yields. There can be a transition period with a yield penalty. I'm not going to undersell the importance of getting farmers through that transition period. That's an area that I think we need policy and economic assistance and research into how to actually shorten to as little as possible. I was impressed that it can be as short as a couple years, but if your farm is on the hook every year, you might not have a couple years. So that needs real social policy attention. But the societal benefits are clear. Less fertilizer use, less pesticide use, less fossil fuel use translates into less pollution, both on and off site and in our water. We can increase the amount of carbon that gets into the soil. All those khaki to dark colored soils I was showing you, that's carbon in the ground. There are wild arguments about how much carbon we could put into the ground agriculturally at a global scale. I tried to parse some of that in Growing a Revolution near the end of the book. My contention, though, is that it almost doesn't matter. We need to do these practices anyway and put as much carbon in the ground as we possibly can. There's other reasons that are equally compelling for adopting regenerative practices. The carbon's almost a bonus. Now, if we could figure out how to pay farmers to put it in the ground and quantify it and account for it, that'd be even better. And we can also get better water retention. So it's my contention that we are conceivably poised on the eve of what I call the fifth agricultural revolution. You look back through history, historians argue about how many agricultural revolutions we've already had. I think there's been 4. If you think there's been 3 or 5 or 10, fine, okay. I'm not that vested in the number. What I am really excited about is the idea that we're poised for a change in the way that we think about soils and that we think about agricultural practices, and that the lens of thinking about soil health as the metric to measure them by is a pretty good lens. Practices that build the health of the soil should be those that we support as a society. Practices that continue to degrade it are those we should stop subsidizing. It's kind of that simple. And I'm excited that we may be at a point where this could play through. All the agricultural revolutions that have happened in the past, none of them happened overnight. They all were a process that played out over decades to centuries. And this transition will take decades to pull off, should we be successful at doing it. But as a geologist, I think that's pretty damn fast. And I'm really excited that at least I'll live, I think, hopefully long enough to see at least the leading edge of a transition. But I think we could pull it off in a few decades. Maybe less, maybe a little more. The important thing is that we get started and we start supporting the farmers that are moving in a regenerative direction. Because I think the more that do, and the more that demonstrate that it works, both to rebuild the soil and also as an economic model, the more these ideas will catch on. And I just want to emphasize, this isn't really a question of organic versus conventional farming. That's a different argument for a different day. These soil health building practices, I think, can help build soil fertility on both conventional and organic farms. And it's basically about adopting the principles of ecology, the science, as opposed to ecology, the advocacy philosophy. There's real science behind why this stuff seems to work. And a lot of that science wasn't terribly well understood when I was in graduate school. It's one of the reasons it's kind of exciting to work on books like this, is you get to sort of refresh your knowledge in another field. Obviously, I'll recommend all my books to people, whether you check them out at the library or buy them here after the fact. Authors love to have their books read. We're thinking about, we want to spread ideas. And I wouldn't have spent so much time thinking about these and writing about these if I didn't think it was important and exciting and interesting. So I'll obviously recommend them to you. And I think we have a panel that's next, which I can hand off to. And if you do want to pick up a copy of the book, the bookstore has them out there. I'm happy to sign them when we're all done.
If you'd like to join us on the stage, the panel members, and okay, if I may have your attention again. So Dean Forbes will be moderating the discussion tonight. Her main research goals are to understand how responses to environmental stress, such as toxic chemicals, link across levels of biological organization, from the molecular to the ecosystem level, and to use such understanding to improve ecological risk assessment and environmental management. And most of her work has involved aquatic invertebrates, and in particular animals that live in and feed on sediments, since this is where most of the harmful chemicals entering the environment accumulate. So Dean Forbes will be moderating. You recognize Dave, you recognize Dr. Anna Cates from earlier, the new soil health specialist. And the new people on the stage are Grant and Dawn, and I should have gotten this name right with you before the stage, Bright Kreutz? Close enough? Stony Creek Farm. Stony Creek Farm is on the Minnesota River Bluff near Redwood Falls, Minnesota, in Delhi Township. And they've farmed there for the past 24 years, during which time they've converted from conventional crop cow-calf operation into a multi-enterprise regenerative family business. They have changed from a corn and soybean rotation to at least a 3-crop rotation with cover crops incorporating wherever they can in their 100% no-till cropping system. They graze with cattle across the landscape, and they use this intensive grazing to manage the pasture system. I will let them say a little bit more about their process while you vote for your final questions, and Valerie welcomes you. You have a microphone, don't you? I have a microphone that is not.
There we go. Now I'm on. Thank you. All right. Thank you to our panelists. Are we like a little long? Could we sort of cozy in a little bit to make it look more like a living room instead of a line? Yeah, that's better. Isn't that better? Isn't that more like natural? But while they're still voting, that's good. That's good. Just to continue, we just heard a little bit of bios, but Anna, you said you were new to Minnesota. Can you say a little bit about where were you before and what were you doing before your current position?
Sure, I just moved from Wisconsin where I was doing graduate work, and before that I grew up in Montana. So those are my 2 home places.
Okay, very good. And you got here in January.
I got here in January.
And you're still here.
Yeah,
That's a good sign.
Wisconsin isn't so different. It is
That's
south,
true.
I know, but not so different.
And Grant and Dawn, how long have you been doing regenerative agriculture?
I would say strongly for the last 15 years. We kind of started out with our cattle operation on our native pastures. We're along the river, so a lot of our land has never been plowed. And we figured out how to quadruple the production on the pastures through managed grazing. And we looked at each other one day and it's like, why aren't we doing this on our corn and soybean and grain operation?
So did one of you have to convince the other, or did you both sort of come to this conclusion together? Tell the truth, Grant. Tell the truth now.
Okay, I will. So when I met Dawn...
Do you want to answer this question instead? Okay.
I'll tell the truth. When I met Dawn, she didn't know how to run a riding lawnmower. And I was in production agriculture big time. I was farming with 2 other farmers. We farmed about 6,400 acres of row crop. We worked 20 hours a day, 7 days a week, all growing season. And the only time she could ever be with me was riding in the cab with me when we were dating. And she kept asking why. So every pass we made on a field, it's like, why are we doing this? And then when we got the opportunity to farm on our own, same questions were coming up, and it just kept me thinking all the time, and it is, why are we doing this?
Okay, good. And are you optimists?
I'm not sure it's optimism. I think it's more of addicts. We're addicted to what we do. I think I saw his passion for, he's just one of these people that was born to be a farmer. And that's what attracted me, was his passion for doing it. But as I was watching everything that happened out there, I was less attracted to what was happening on the land, in doing the tillage and the row crop part of it, and more attracted to the animal side of it. And so for me, I was like, why can't we just plant this all to grass? Well, economically, that just isn't something that you can do overnight. And now I'm seeing that might not necessarily be the right answer either. So we're kind of finding a mix of the two, but ultimately I'm more the cowgirl than the row crop person.
Okay, good team. I like that. Now, see, we only have 4 comfy chairs here, which means I get to sit on this stool, which hopefully I won't fall off. It does mean I get to be taller than everyone for a chance, so that's good. They seem to have voted, so I will read the first question. What is the single most important thing we can do we can go now to help restore the soil in our own gardens and properties. And that's open to anyone who has a view on that.
Anyway, I do have views on that, and I would say composting and mulching is like a big thing. And if I am continually perplexed by people who clean up the leaves in their yard and put them in the leaf bag and send them off somewhere else to fertilize someone else's yard. So, if you're doing that, stop. Your trees are trying to recycle their own nutrients to feed themselves. So composting and mulching, and basically building up your organic matter. And the nice thing is that if you have a source of it, you don't need to dig it in. Leave it there. Let the biology do the work for you.
Other recommendations, thoughts from any of you? Yeah.
Well, my thought would be is if you're tilling it, quit tilling it. That's what we've found in our farming operation and even in our garden is once we eliminated tillage on our farming operation, that's when our corn yields increased and everything else increased at the same time. But what we noticed was the biology in the soil just kicked into overdrive then.
So you're not recommending zoo poo?
Oh, well, if you have access to Zoodoo, sure, it's good stuff. Yeah, if you think about, what kind of organic matter you have access to in a city, Zoodoo is one of the few places of like real manure, real sort of biologically inoculated herbivore stuff. Although we did legalize keeping, I think, 12 chickens and up to 5 or 6 goats in your yard in Seattle a few years ago. I just don't know if I recommend living next door.
All right, well, let's go to the next question. To value maximum yield, any thoughts on ways of influencing producer decisions that allow for better conservation?
How long are we going to sit here tonight? In my mind, the biggest problem we have in this country right now is our farm bill. As a producer, as David mentioned earlier, a lot of us are getting strapped financially. Our ag lenders force us to plant corn, soybeans, which are the two highest insurable crops we can plant as a farmer, which takes the diversity right out of our cropping rotations, which then affects soil health and everything going with it. So to me, that's one of the key things right now. And the other thing would be is finding markets for the other grains. They're out there, we can find them. It just takes us a while as a producer.
I'll just add to that a couple of things. One is that this is talking about maximizing yield, and Dave brought this up during this talk, but we should be thinking about maximizing profits, not yield. And I know you guys think that way. So bushels are not the ultimate goal, right? Dollars are the ultimate goal for a business person. So that's one piece. And then the other I would mention is, Grant mentioned the Farm Bill, and we talk a lot about approaching this problem as consumers. What can we eat that's directly purchased from farmers, and that's a great way to approach it. But the other way to approach it is as citizens. We all have access to our representatives who work on the Farm Bill. So if you get educated on that and let them know your feelings about it, that's the other way that you can push on this issue.
Just to add right back to that, the profit per acre is that's when it changed our operation 100%. When we quit looking at production and just went to profit per acre, we thought we were going to lose some production, and at times we might, but we're also realizing those dollars back in our livestock because we had ran our livestock across there and harvested $40, $50, or $100 an acre and only took $20 or $30 an acre less cash grain. So in all reality, we're producing more profit per acre now than we ever have.
Interesting. It surprised me that idea hasn't caught on more broadly. I mean, it seems that that's where you would feel it in your own pocketbook. And some of the examples you had in your presentation, it's kind of surprising that more farmers aren't, saying, "Hey, wait, I want to be part of this."
Well, 10 years ago when I wrote the Dirt Book, nobody was talking about soil health. And so if you look at sort of the changes in just the number of people who've been thinking about it and adopting it in the last 10 years, it's actually pretty astounding. It's still on the growth part of an adoption curve, but it's been moving up. And yeah, I was curious about exactly the same thing interviewing people, but I think it's really hard to ask people to change the way they've been doing things. And if you've been taught and learned that something is not possible, it's really difficult to see the evidence that it is.
Have you seen this with any of your neighbors, colleagues, or?
The biggest part about change as a farmer is we've been taught generation after generation how to do what we're currently doing. As farmers, it's known industry-wide that 85 to 90% of a farmer's input decisions on his farm are usually based off of what his input supplier tells him to do, which is our fertilizer, our seed, our chemical dealers.
It's like conflict of interest there on their part, maybe?
Yeah, it's a big conflict of interest, but at the same time, as a producer, we've been doing it this way for 20, 30, 40, 3, 4, 5 generations. All of a sudden, when we change to this style of farming, we're admitting we were wrong. How easy is that as a human being to admit that we've been wrong?
Yeah.
That's what makes it tough for people to change.
Can we have the next question, please? Maybe you two could share, Anna and Dave. Okay, we're going to the next question. How do soil erosion rates differ for rangeland versus cropland? And what role do you see for grazing of animals in a global food production system that produces food and maintains soil? That's a really long question. Do you want me to read that again?
Sure. I mean, that's a really good way to limit erosion is to keep the land covered with plants. So if you have rangeland that's not overgrazed, it's probably not eroding badly. You can graze it to the point where it'll erode badly. That's been done. But if you look, so it really depends on how you graze it as to what the erosion question is going to be. Kind of the same way with like how you farm, how you deal with crops. In terms of the animal production part, yeah, I think my view on that has evolved somewhat, but I look at it today on sort of a macro biogeographic level, where if you look at the best way to grow food for people in different regions of the world, there are areas where livestock makes a ton of sense. And that's sort of the native grasslands of the world. Why? Because we can't eat grass. Cows can, and then we can eat the cows. We can eat with the milk. We can eat the cheese. Now, there are places where you can convert grasslands into croplands, but part of the sustainability issue on that is what your water supply is. And one of the really nice things about animal agriculture, about livestock, is in semi-arid regions of the world, you can sustainably produce a lot of food for people that way. Now, it's all about how you raise the livestock. It's about how you farm. And I'm finishing up a textbook on sustainability where I've had discussions with my co-authors and discussions with the publisher about, how do you deal with what would be a sustainable diet for humanity and what's the role of meat in that? And my position has evolved. It really depends on how the meat is raised. Sort of where it's raised and how it's raised is the real answer. And raising a lot of meat in feedlots fed corn in ways that where the corn is grown with erosive practices, I mean, it's like bad compiled upon bad. On the other hand, you look at the nutritive value of grass-fed beef relative to corn-fed beef, and there's an awful lot of studies that have documented some pretty serious differences nutritionally that translate into potentially translate into human health. So the idea of eating meat as part of a healthy diet is sound, depending on how the meat was raised, where it was raised. So that's sort of how I look at it, is that it really depends. It's just like with the cropping systems. The real answer is that it depends how you do it.
Yeah, anything to add? Yeah, because you said you have livestock, don't you?
Yeah, we have cow-calf operation, and like I said, that's where we started. We figured out how to groom and actually landscape our cricks, and we've got 10 cricks that flow through our grazing allotments. We re-groomed those with the cattle. There's a way to do it. We secured all of our stream banks through grazing. Rest, recovery, that's how you do it. Until last year when our neighbor's water came through and took it all out. So it was good for us. We fixed a lot of things, but yet it's people upstream from us that cause a problem. But the key part that we've learned about the livestock is that is the fastest way to regenerate soils. We can take a depleted piece of soil on our land, and we've done this systematically through our farming operation. You can take a spade, dig out the biggest chunk you can dig out. You can find 1 to 2 earthworms in that spadeful. We run a small grain crop. We harvest that for grain. We bale all the straw off for our cattle. We come back in there with a 9 species cover crop. We graze it during the winter months, taking half of it off, leaving half of it there for cover. It greens back up in the spring. It's holding our nutrients that the cattle dispensed out there. And at the same time, we'll flip that same shovel full of dirt over and have 16 to 20 worms in it. In basically less than a year.
That's pretty dramatic.
Worms are our largest indicator of soil health. It's the simplest, fastest, easiest.
I love worms. All right, very good. Next question. What's the potential for water quality improvement in the rhizosphere if we route urban stormwater to plants, especially trees, root zones? We should be talking about water here tonight a little bit more. I feel an obligation, John, you know.
Well, I'm not quite sure what they mean by water quality in the rhizosphere in particular, but
You can use artistic license.
Yeah,
Just
certainly.
interpret it however you want.
certainly moving stormwater to plant roots instead of to impervious surfaces and eventually the drainage system would be a huge improvement in terms of keeping nutrients on the landscape, keeping nutrients out of the waterways. In terms of how trees would respond to that stormwater in particular, I don't think I can speak to that.
Might depend a bit on what's in the stormwater. And that's where, you know, is it coming off a road? Is it coming off a roof? It might really depend on where the water's coming from.
Good point, yeah.
I guess just to add to it from the ag side of it is, on our farm, we've done countless amounts of testing. Kent Solberg's here. He's helped us with a bunch of it, Dr. Alan Williams, and others along the way. And we're at, on average on our soil, we're between 8 and 12 inches per hour of water infiltration ability on our farmed land where we're growing cash grains. We can step right across the fence to our neighbor who farms conventional, and it's less than an inch per hour.
Wow.
All this flooding we're having, everything we're having, just imagine if we changed the landscape like that.
Make a big difference. All right. Let's go to another one. How can we convince landowners to restore wetlands to keep water on the land? Oh, there's a question.
Well, with what I just said, we won't have those wetlands unless they were actually a true native wetland and remove the tile to get it back there. But we're seeing it in our native pastures where there's never been a tile, there's never been a plow, where we dealt with pastures that we couldn't use because the water was too deep, it was too mucky to move cows through this area.
Yeah,
We no longer have those issues. We're holding the water up on the hill where it's meant to stay.
okay.
So that our bottoms are actually, our holes, I would call them, prairie pothole region, are actually drier. But yet we have springs developing up higher in the hills, water coming out of the sides of the hills I've never seen in my lifetime. I've been there for 50 years. My dad's never seen it. When we put the water back in where it's supposed to, it stays where it's supposed to. It grows massive amounts of grass on hills that we never used to grow, and yet we still got all the wildlife and everything working in the whole system.
Indeed. So, in other words, to answer the question, we just need that landowners to hear your story. How could they not be convinced, basically? Have you thought about co-writing a book together, you guys here? I have an idea.
I will say about this question, how can we convince landowners to restore wetlands? It is coming from a place of telling landowners what we think they should do. And I think some of the most successful conservation efforts on the landscape look at farmer-led groups and peer mentoring and that kind of thing. So sharing stories among people who are also working the land. But this is $1 million question, so if anybody has a great answer out there, I'm interested.
I mean, I think that's a really good point, and that came up in one of your earlier examples, that there's no one solution for everywhere, right? And so you can't have knowledgeable people from one part of the world telling other people what's going to work for them, because it's probably not. I mean, that's I think, a really important take-home message. All right, let's take one final question. I know the audience has been sitting there very patiently, and I'm sure you want to talk to our speakers afterwards. Final question. Oh, good. I like ending on hope. What are you most hopeful for looking forward to in this arena? What gives you the most hope moving forward?
I'll point to two things, and one I sort of alluded to earlier, but that's sort of the momentum I see behind these ideas as growing. And if that momentum can keep up and accelerate the change, I think we'll see some big changes in the next 10, 20 years. And if it happens at that pace, that's really fast. So that gives me hope, and I think that we could pull that off. You know, we could get to the point of half of North American agriculture being regenerative in 10 or 20 years. Will we? I don't know. Nobody knows. Anybody who predicts the future is, crazy. But I think it's feasible, and that gives me hope that we could do it.
Well, being new in the state, I've had the fun of calling people all around the state who work in soil health and asking them questions about their job. And every time I get off one of those phone calls, I feel more hopeful because of all the people who are working hard in this arena. And I'm just the latest to the scene. So I really appreciate people sharing their knowledge with me. And I feel like we've got a great foundation to work from.
I guess the session we had here this afternoon kind of gives me hope that there was that many stakeholders there of all different, schools, independent, whatever, and farmers there that are looking at this. I guess in our local area, the one thing that's pushing this, that's going to, in a sad way, give us hope, is the economics of farming right now. We actually have real good friends of ours that we've worked with in the livestock side of the operation that last year came to us and said, we're not hooking up to a single piece of tillage equipment, teach us how to do this. We had another member of our church that we've gone to church with for 21 years, and he's heard us discuss this in the back of the church, me and one other guy that no-till for 15 years, and he pulled into our yard 3 weeks ago and he says, I'm ready. So it's changing slow but sure.
One of the things that that we talk about when we travel and we talk to other people of like minds is that we've watched the population of the ag community decrease so rapidly, and our communities are dying because of it. And I guess I'm hopeful that in this movement we rebuild these communities and not the communities within our families and then out on the landscape. And that we do have something positive to pass on to generations to come. Because in the time that we've been together, it's gone from us almost walking away from the farm because it was just getting to be too much and it was depressing and we were losing money, to farming becoming fun again. And knowing that we're doing the right thing. And so we just have to hope that that movement and that passion continues to grow and just keep moving forward. So.
Thank you. Thank you very much. Well, thank you all. That was a very engaging discussion, great presentation. Thank you to the audience for your participation and enthusiasm. And please join me once more in thanking our panelists and speakers.